So hello everyone, myself Sudhanshu Kumar, pursuing Master in Chemistry from IIT Indore, and today we will discuss about the very important chapter that is a free radical, okay, in the organic chemistry, right? And and I am taking all the questions here, like you can see here, lots of questions I am taking here. These are all the questions I have taken from Clayden. Okay, that's a very standard book. I hope you know this. So I am writing here Clayden. Okay, Clayden. That's a very standard book. Okay, of organic chemistry. A standard book. I must recommend you to go through this. Okay, must, right? So before starting this, I want to tell you we have a Telegram channel. You can join there. Okay, all the notes, PDF, etc. All the things are available there. Okay, I have already uploaded. Okay, so don't worry about that. So I will give the link of a Telegram channel in the description box. Okay, so now let's start. And yes, so please make sure that you have subscribed my channel. So please like, share and subscribe my channel so that I will get a motivation and try to upload more videos like this. Okay, so, yeah, so let's start. Okay, so the first thing is so I am telling all these things. This is my personal notes. I have made this personal notes from this book, Clayden. Okay, that's a very standard book. Go through this. Okay, so take a notebook and pen, and if you want to take a notes, then you can take also, right, with me. Okay, so let's start here. Suppose you have a HCl here, and the medium is a gas phase, right? So you will never get a H plus and Cl minus in the gas phase. Okay, you must have to keep this in mind. Okay, suppose you have taken HCl and you are expecting that it will break into H plus and Cl minus, then it can't be happen. Okay, so if you ask me, so when the HCl will get dissociate into H plus and Cl minus, so the answer is HCl will get dissociate into H plus and Cl minus only in the solvent. Okay, only in the solvent, right? Otherwise, in the gas phase, you will never get H plus and Cl minus. So that's why I have made a cross here. Okay, this is not possible in the gas phase. Now, if you have taken a HCl and the temperature is greater than 200 degrees Celsius, then you will get a radical, H radical and Cl radical. It means this HCl bond, this bond is breaking homolytically. Okay, so that's why it becomes the H radical and one is the Cl radical. Now see how to make a radical, what is the different methods to form a radical. Okay, so how the radical is formed. So the first method is homolysis of weak sigma bond, right? So I hope you know this. O single bond O, this bond is a weak bond, right? O single bond O is a weak bond, right? Weak bond. So that's why you can do a homolysis of this weak sigma bond. So this bond will get break as a homolytically. Okay, and then you will get two molecules of a OR radical, right? Now see, this is the first method. Okay, this is the first method to make a radical. Now the second method is electron transfer method. Okay, that is basically a reduction. Okay, and you can say this is the addition of electron on the electrophilic species, right? So see here we have C double bond O, right? Here we have C double bond O here. So and you know that this carbonyl is act as a electrophilic center. It means this carbon is acting as a electrophilic center. So that's why what happens, this electron will go here and this pi bond will go to shift on this oxygen as a negative charge, and now you will form a radical something like this. So this is also a method to form the radical, right? That is called electron transfer. So till now we have studied two methods to form a radical. First is the homolysis of a weak bond, weak sigma bond, and the second method is the electron transfer method, that is also called a reduction method, that is also called addition of electron. Now you see, you can generate a radical from another radical, okay? This is also you can do, right? Like how to form a radical by radical. It means कि हम एक रेडिकल से दूसरा रेडिकल कैसे बनाएं, इसके भी तरीके होते हैं. इसके होते हैं तीन तरीके. पहला क्या? Substitution. Second one is addition. Third one is elimination. Okay. Now see, first of all, substitution. And you can say substitution is also a obstruction. Okay. So see here, we have already a radical, X radical, and this is a bond here, YZ bond, and this radical will take this Y, okay, and that's why this bond will gonna be homolytically cleaves as a Z radical. So you can see here, we have already taken a radical, and now you are forming a different radical. So that's why I am telling you, a radical from other radical. It means we have taken here X radical, but in the product we have generated Z radical. It means this radical and this radical are different. So it means we are generating a different radical from a radical, right? Now see, the second method is the addition. So in the addition, you can see here we have a double bond here, right? So this radical will simply add on this one, and this bond will be, and this double bond will be gonna break as a homolytically on the Z atom. Now we will find something like this. So here you can see also, here we have a X radical. Now you will get a different radical, G. Okay. Now see, the third method is the elimination, that is done by a homolysis. So suppose you have something like this molecule, a species. So this is a X radical, and this is a sigma bond between this X and Y, and now we have sigma bond between the Y and Z. Now what happens? This radical will combine to this Y, and this bond will gonna shift on something like this. Okay, so that's why you will form a X double bond Y here, X double bond Y here, and plus Z radical. So this is the three methods we have discussed till now to form a radical from another radical. Okay, now see, this is a stability order. I hope you all know this. So basically, generally we compare the stability of a radical by the hyperconjugation. So that's what I am doing here. Suppose we have something like this one, this one, this one. I hope you know the hyperconjugation. What is the hyperconjugation? So it means so more the alpha H, okay, more the alpha H, it will be more stable radical, right? So that's why if you see in this case, so we have CH3 here, CH3 here, CH3 here. So that's why here is a 9 alpha H, right? And in this system we have 6 alpha H, and in this system we have 3 alpha H, and in this system, let me wait, yeah 3 alpha H, and in this system we have 0 alpha H. So that's why I have told you, the more the alpha H, the more the stability of the radical. So that's why this 3 degree radical is a more stable. So that's why the stability order goes to one like this one, then we have this one, and then we have this one. Okay, now see, if you have something like this, like alkyl radicals, okay, like radical next to double bond, okay, radical next to the double bond, like this. So this can be form a रेजोनेंस स्ट्रक्चर. कैसे होगा? ये ऐसे होगा. ओके, so that's why it is a more stable. Okay, so it is more stable than the alkyl radical also, right? So these are the so we are basically seeing here like this. Suppose, wait, see here, we have discussed till now, these are the alkyl radical. Let me write here alkyl radical. These are alkyl radicals, right? Okay, now see, this is the allyl radical. Allyl means next to the double bond. It means radical next to the double bond. So that's why it will be a more stable than the alkyl radical, because it can form a resonance structure. How it is possible? See here, this bond gonna here, okay, and this bond gonna here, right, and this bond gonna here. So you can form here something like this, something like this. This is a resonance structure between this one. Okay, so that's why it is a more stable than the alkyl radical. Now see, if you have a double bond radical, triple bond radical, like phenyl radical, these are very less stable than the alkyl radicals. Okay, right. Now see, one more note, very important note here. So radical next to the carbonyl, nitrile or ether functional groups or a centered carbon atom are more stable than even a tertiary alkyl radical. Okay, suppose you have radical here, tertiary alkyl radical, something like this, CH3 here, CH3 here, and I am taking also something like this. These are all the radicals, but these radicals we have on this radical in the adjacent position, we have a functional group here, C triple bond and C double bond and OET, right? So this is the C double bond O. So if you can see here, so these are the more stable than the tertiary radical, than this alkyl radical. Okay, so that's what I want to say. Like if you have a radical like such radical in which there is a next to the radical we have a functional group, either it can be electron donating and either it can be electron withdrawing group. It doesn't matter, it will always stabilize the radical. Okay, so that's why what I want to say here. So if you have such radical next to carbonyl, nitrile or any functional group can be either electron withdrawing or can be electron donating, it doesn't matter. Okay, so both types of functional group, either it can be electron donating or either it can be electron withdrawing groups, will stabilize the radical. So that's why in this case, these all the cases, let me erase here, okay, then you can feel. So these all are more stable than simple alkyl radical. Okay, so keep this in mind, right? Now see, radicals that are stabilized by an EDZ and EWZ group at the same time are sometimes known as a cathodic radical. Okay, it means something like this. We have radical here something like this, and you have C double bond OH group here, and here you have OMe group. Like this radical, just इस रेडिकल के बगल में हमारे पास यहाँ पे फंक्शनल ग्रुप है, और ये जो फंक्शनल ग्रुप है ये हमारा क्या है, OMe है. दिस इज अ इलेक्ट्रॉन डोनेटिंग ग्रुप, राइट, एंड दिस इज अ इलेक्ट्रॉन विड्रॉइंग ग्रुप EWZ. इट मीन्स अगर ऐसा केस आ जाए जहाँ पे रेडिकल के बगल में दोनों टाइप के फंक्शनल ग्रुप हो, तो यहाँ पे क्या होता है, इसे क्या बोलते हैं, कैथोडेटिव रेडिकल्स. ओके, या और हाँ एक चीज़ और कि रेडिकल्स को इलेक्ट्रॉन डोनेटिंग ग्रुप भी स्टेबलाइज करते हैं और इलेक्ट्रॉन विड्रॉइंग ग्रुप भी स्टेबलाइज करते हैं. ओके, इट डजेंट मैटर कि वो हमारा इलेक्ट्रॉन विड्रॉइंग है या वो इलेक्ट्रॉन डोनेटिंग है, राइट. नाउ सी, one more factor is asterisk hindrance is also a factor that makes the radical less reactive. Okay, so you can take a note in this mind, in your mind. Now see how the radical react. It means how the radical react. Like radicals की reaction कैसे कैसे हो सकती है. See here. So radical can generally react in the three way. Okay. Yeah. In the three way. So suppose this is the first away, like radical plus radical. They can combine each other and form a spin paired molecule. Suppose you have a Br radical and you have another Br radical. So this Br radical and this Br radical will get combined and you will get a new molecule that is a Br2. Okay. So in that way the radical reacts. So this is the first. Okay. Now see the second one. Suppose you have a radical here and you have a spin paired molecule, right? So what happened? This radical will can abstract this hydrogen as a radical, and you will get a new radical R2, right? So here is a ROH plus R2 radical. Now see a third method is a third away. This is the third away, like how the radical reacts. Suppose you have a radical, so you can generate a radical to a new radical plus a spin paired molecule. Suppose you have something like this, RC double bond O radical. So this radical will gonna sit here, and this bond will gonna break something like this, homolytically, and you will get R radical plus CO2, right? So here is a driving force is a CO2, okay, because here CO2 is releasing here, so that's why this is the driving force of this reaction. That's why this bond is breaking as a homolytically. Okay, you have to understand, you have to pay attention to what I am trying to say. Okay, otherwise you will be in the big trouble. Okay, if you have any doubt you can ask, and please subscribe my channel. Okay, please subscribe my channel so that I will get motivated and try to upload more videos, something like this. Yeah. Now see, suppose you have a RC double bond OR. Now coming to the reaction part. Okay, all the reactions related to free radical I will discuss here. I have taken all the questions from which book? That's a very standard book that is called Jonathan Clayden. That's a very good book. I must recommend you to go and study this. You will fall in love with this book. Okay. Yeah. So now I start. So see here we have something like this here, RC double bond OR, and you know that because C double bond is a electrophilic site here, so that's why this electron will go here and you will form a here cation radical anion, right? Cation radical anion. Okay. So if you ask me this electron is coming from where, it means कि यह जो इलेक्ट्रॉन है कहाँ से आ रहा है. तो इसके लिए हम क्या करते हैं, we take a electropositive metal, okay, in the solvent, okay, like we have taken here Na sorry. तो आप यहाँ पे ले सकते हैं सोडियम, मैग्नीशियम, जिंक और एल्युमिनियम. ओके, सो you can take any electropositive metal so that it can lose electron, and that loose electron will go here. Okay, so you have to take a sodium, magnesium, zinc, aluminum in the solvent, right? So that's why because you know that electropositive metals will lose electron, and that loose electron will go here and attack on this carbon, right? I hope you understand this. Now see reaction of a cation radical anion in a protic solvent. Okay, see here we have something like this. Okay, fine. Yeah, so basically what happened here, so this is a interconvertible into this one, I hope you know this, how to do this. I will not tell you such simple things. This is very simple, okay? You can try. If you don't get, let me know in the comment box. I will tell you this step. How is it occurring here? Okay. Now see, we have ETOH here. ETOH. Now what happened? See here. Now this negative charge will take proton from ETOH. Now you will find something like this. Okay. Now again the electron will come. Sorry. Again this electron will go on oxygen, right? So that's why this oxygen will get a negative charge here. And after that, because we have taken here protic solvent, so this O minus take a H plus, and you will get a alcohol here. Okay. Now see, suppose you have a C double bond O here, acetone here, right? And we are taking here magnesium in the benzene solvent, right? In the benzene solvent. Okay. See here what happened. You know that magnesium is a electropositive metal, right? So that's why it will lose electron, something like this, Mg2 plus 2 electron. So the first electron will go here, right? Attack on this, bond will shift, you will get something like this. After that what happened? See, you have another molecule in this reaction, ऐसे है ना, तो इसका जो दूसरा इलेक्ट्रॉन था वो हमारा इसके पास गया है, right? It will become something like this. O minus, here is a radical. Now this molecule and this molecule will get dimerized, right? So I have done here, see here, this step. Let me erase this. See, this molecule will dimerize itself with another molecule, and now this bond will get joined together. Okay, now you will find something like this, and after the hydrolysis workup you will get this. Okay, now see this one. See here. So here we have taken here aluminium Hg, right? Aluminium Hg, benzene. So the same process here. Aluminium will donate the electron to this carbonyl, right? Okay. And after that, this molecule will dimerize itself. Okay. After that, see here what happened. This molecule will get dimerized itself. We have another molecule in the solvent, O minus here. O minus here. Now this molecule will get dimerized, and you will get something like this. After the dimerization and after the workup, you will get like this. Okay, and 60% of the mixture will get form an anti-diastereomer, because you can see here this OH and this OH are on the anti side, right? So this is the major product here. This is the major, and this one is a minor. Okay, so this OH here and this OH here on the same side. Okay, so this is the minor product. Now you can see here the next question here, TiCl3ZnCu. Okay, I hope you know this. By seeing the reason, you can tell the name of reaction. So this is basically Mach-Murray coupling reaction. Okay, Mach-Murray coupling reaction. I will tell you in detail. Okay, so don't worry about that. See here, so this question is basically Mach-Murray coupling reaction. Okay, but see, for now leave this question. Now come to 1210. Okay, then I will go to here 1209. Now see, if you take a carbonyl, ketone, and you have taken the TiCl3 here and plus LiLH4, okay, Now what happens? Now you will get the product this. This is our product. But how we get this product? What is the mechanism? See here. You know that LiLH4 is a reducing agent, okay? So its work is to reduce the other, right? So that's what here LiLH4 do. So this LiLH4 will reduce this Ti3 plus into Ti0, right? And then the Ti0 will lose electron. Then the Ti0 will become Ti2 plus by losing the 2 electron. Okay, so that's why what happened now, the Ti will lose the electron. So Ti0 here, it will lose the electron, 2 electron. So here the 1 electron goes on this one, right? Okay, and now this molecule will get dimerized into the same molecule, something like this, and after that you will get something like this. Okay. Because here is a we have a titanium metal here, so we have to remove this. Now what will we do? There is a process deoxygenation on the surface of TiO particle, Ti0 particle, right? So we are basically what we are doing here, we are just removing this as a on the titanium metal. Okay, so this step is called deoxygenation, and you will get a product something like this product, and this is called Mach-Murray coupling reaction. Mach-Murray coupling reaction, because here two molecules are coupled each other. That's why the name of the reaction is the Mach-Murray coupling. Mach-Murray is the scientist name. Okay. Now see the 1209. See here. But one more side product. What happened? See here. If you do this reaction after this step, if this reaction is happening at a low temperature, okay, if this reaction is happening at a low temperature, then you will not get this product. You will get something like this. See here. You will get something like this. This is at the low temperature, at low temperature. Okay. If in your question mentioned at a low temperature, then this will form. Okay. This is also observed. Okay, right. But in the question, if you have nothing written about the temperature, then just do the Mach-Murray coupling reaction. Like you have to form this product. Okay. Fine. Now see this question. We have here CHO. We have here CHO group. Now we are taking a ZnCU PiCl3. Now you know that ZnCU ZnCU will work as a reducing agent, right? So this will reduce the Ti3 plus to Ti0, right? And this Ti0 will lose the electron and attack on this CHO and this CHO, and now the both CHO will get dimerized, and now after that you will get something like this. Okay, here in this question the double bond will not form, okay, because this reaction is done at the low temperature. So if you done at a low temperature, then you will not get a double bond here. You will get a simple cold type product. Okay. Now see this one. This is the same reaction here. Okay. ZnCU is a reducing agent. You know this. This will reduce the Ti3 plus into T0, and then the T0 will be lose electron and attack on this carbonyl, and bonds get shift, and then this molecule will get dimerized into itself, and you will get a final product like this. This is also a Mach-Murray coupling reaction. Now see this one. This is the same question here. Now we have TiCl3 ZnCu. It will reduce the Ti3 plus to T0, right? So if you write here TiCl3, this is in the plus 3 octahedral state, and if you take here ZnCu, it will become Ti0, and this Ti0 will lose 2 electrons, and this electron will go attack on this carbonyl here and here, and now this both molecule will get dimerized, and you will form a something like this compound. This is your product. Flexibilane इसको बोलते हैं, flexibilane. Okay. Now see this molecule, this reaction, see here, this is called basically acyclovine condensation. Acyclovine condensation. Acyclovine condensation. So in this reaction, what happened? See here, you have something like this. Here we have sodium here, right? Sodium. You know that sodium is a electropositive metal, so that's why it will lose the electron, and when it loses the electron, Na plus electron, and this electron will go here, and you will find something like this. Okay, and both molecule will get dimerize itself if there no amine molecule present in the reactant, then it will dimerize with itself. Okay, this is called radical dimerization. Okay, now you will form something like this. This is the unstable product. Okay, so what happened? This O minus gonna come back, and this is the living group, so it will leave. Same process here. O minus gonna come back, and this will leave, and after this you will form a 1,2 diketone. But the reaction did not stop here, because still we have electrophilic center, so that's why the reaction will not stop here. After this, see here, after this again the sodium will come, again the sodium will donate the electron to this carbonyl, and you will form something like this, and then what happened? The bond will get break homogenetically, and after that you will get a product like something like this. This is very easy. Okay, I have done all the mechanism, all the step by step, so that you can understand. Okay, so keep in mind, so please keep in mind, the reaction will not stop here. Okay, it will go forward more like this. After that, the sodium will again donate the electron to this carbonyl. Okay, yeah. Now see the next question here. So here we have sodium, toluene here is a solvent, Me3SiCl is a electrophile, right? Now what happened? This Na will lose electron and attack on this carbonyl, C double bond OET, right? Same here, attack on this carbonyl, and then what happened? This get both combined here. Okay, combined, and you will form something like this, and after that, because we have living group, so that's why the O minus will get come back here, and this bond will get leave, and same here, bond get come back and it will leave. Now the same process here, because this reaction did not stop here, because still we have a electrophilic center, so that's why the sodium will again come and do the reaction as usual. Okay, and form again a radical, right? So what happened now? See here, because see you have here O minus Na plus, right? O minus Na plus. So what happened? And you know that silicon is a hard electrophile, and the O minus is a hard nucleophile. So what happened? This O minus will attack on the silicon, right? Because we know that hard to hard reaction is more favorable. Okay, hard, soft. Okay, this is the HSAB concept. Okay, I hope you know this. So that's why O minus will attack on the Si, Cl will leave, same here, you will form like this. You will get this, okay. And after that, what happen? This radical both get combined here, okay, and you will form a double bond here, right? And you will get your final product. This is your final product. Okay. Now see the second question. Next question here. Suppose you have toluene here. Sodium, again the same function. It will donate the electron here, here, and after this both will get combined. Okay. And you will get form here something like this. Same mechanism as we have done this one. Same means the question is different, but the process, but the method is same. Okay. Now see this question. This is we have double bond here, right? And we have taken here HBr and in the ROR HU. Okay. Now see how this is forming. How we get this product. What is the mechanism here? See here. First of all, you know this ROOR, and we know that this bond is a weak bond, so that's why in the presence of light this bond will get break homolytically and you will get a two molecule of OR radical, right? And this radical will abstract the proton, will abstract the H radical from this HBr and you will get a Br radical, okay? And this Br radical will attack on this double bond, and this double bond, so this double bond will gonna break homolytically and shift on this carbon as a radical. Now you will form something like this, okay? Now this radical will take a H radical from the HBr and you will get a product like this, okay? Yeah. So this is the mechanism of this reaction. This is a very simple mechanism, okay? These all reactions we are studying from class 11-12, okay? See here, in each step cycle a radical is consumed and a new radical is formed, and this type of reaction is therefore known as the radical chain reaction, okay? Right. Now see, radical chain consists of 3 steps. First is a initial step, that is called initiation also, right? Initiation. And the second step is a propagation step, and the last step is a termination step. See here what happened. So this is our first step. This OR bond will get break as a homolytically and you will get a OR radical, right? And this OR radical will take a H radical from this HBr and you will get a ROH plus Br radical. Now see, we have a propagation step. What happened? This Br radical, okay, now this Br radical will get combined to this double bond. This is the basically addition, okay? This is the addition here, addition of Br radical, right? So this Br radical will add on this carbon, right? So that's why this double bond will break as a homolytically and it will form something like this. And you know that this radical is a more stable, okay? This radical is a more stable. Suppose anyone asking like why we cannot do this, like Br radical, why not attack here, why this is not possible? So if you do, then you will get a 1 degree radical, okay? If you do this, then you will get a 1 degree radical, and if you do this, then you will get a 3 degree radical, 3 degree, right? So that's why it is a more stable. So that's why we cannot do this, right? I hope you know this. So then this will take H radical from here, from HBr, and you will get a form something like this. And you know that the most important step is a termination step, because termination steps are actually important part of any chain reaction. Without termination step, the reaction would be uncontrollable. So to control the reaction, we have to do in the last, we have to do termination effect. It means we have to uh, kill the radical. It means we have to combine the radical into a spin paired molecule, right? Now see, we have see here the next example. This is a halogenation of alkane. Halogenation of alkane. Right. See here, we have something like this cycloalkane here, and I have taken here Cl2H2. So what happened? First step is initiation. So this Cl bond get break as a homolytically, okay, form a Cl radical. After this we have a propagation step. In that what happened? The Cl radical will take this H radical, right? And then this bond will get break as a homolytically, and you will get a radical. Now after that, we have a Cl2 here in the molecule. We know that. So that's why this radical will take a Cl2. This radical will take a Cl radical from Cl2, and then you will find something like this. And now we know that the last step is a termination. So that's why this is a termination step. One second. Yeah. So Cl will combine each other and make a Cl2. Oh, sorry. Yeah, now this is fine. Okay. Cl2. Okay, so this is the termination step. Now see this one. If you have alkane here and Cl2H, okay, so what happened? See here, we have H here, so Cl2 will get dissociate into Cl radical, and this Cl radical will take radical here, right? And you will form something like this, and this radical again combine to Cl radical, and this Cl radical will break, and you will form something like this, okay, this one. So you will get a major product, this 55%. But if you take 2 degree, like here is a hydrogen, right? Here is a hydrogen, here is a hydrogen, okay? So if you have 3 degree hydrogen, right, then in that case this will be major product, okay, and in this case this will be this is a minor and this is a major will be formed. ये ऐसा क्यों हो रहा है? तो ये ऐसा इसलिए हो रहा है ड्यू टू selectivity and reactivity. Okay, see, if you see the order F2 Cl2 Br2 I2, F2 is a more reactive, then Cl2, then Br2, then I2, right? So less reactive will be more selective. I hope you know this. Okay, so in the comparison of a Cl, because we know that the Cl will show selectivity. So that's why if you have 2 degree hydrogen, then the halogenation will be preferred at the 1 degree. Okay, then the halogenation will be preferred at the 1 degree hydrogen, and that will be the major product, because the Cl2 will work as a selectively. It means it will select the position. Okay, it will select the position. It means it will choose the least hindered hydrogen, and then do the reaction, right? So in such system, you have to take care of this. This one is important and this one is important. Okay. Now see, if you take a Br2, right? If you take a Br2 here, and you know that Br2 is a more selective, right? Br2 is a more selective because this is a less reactive than Cl2, right? So that's why in this case what happened, see here, yeah, in this case you will get 99% mineral product of this one. Okay, in this case this hydrogen will, Cl radical will abstract this hydrogen, and then you will form a radical, and then Cl2 will come, then the Cl2 will come here, and you will form something like this. Okay, and this will be the major product. So you have to keep in mind, if you have Cl2, okay, if you have Cl2 and you have possibility of this is a 2 degree H and this H is a 1 degree H, right? So in that case the Cl2 will prefer to this is a 3 degree H. Okay, sorry, yeah. So in that case this Cl2 will prefer to do the reaction at here 1 degree H, and this will be the major product. Okay, now see, we have NBSCCl4. This is a allylic bromination. Allylic bromination. Okay, so what happens if you have a double bond here, something like this, and you have taken NBSCCl4 and H mu, then you will get a product like this. Okay, but how we get this? What is the mechanism? See here. So what happened? So H mu, we have taken the light here. So what happened? This bond will get break as a homolytically. Okay, homolytically. This will form something like this, plus Br radical. Okay, and this is a Br radical, and now this Br radical will abstract this hydrogen radical next to the double bond, because this allylic H is a weaker bond. This allylic H is a weaker bond. That's why this CH bond will get abstracted by this bromine radical, right? And you will get a radical. Okay, and after that you have a Br2. Okay, right, and then you will get a product something like this. Fine, yeah. So this is called allylic bromination. I hope we all have studied from the class 12 already. Okay, now see this. This is our NBSCCl4. What happened? The same procedure here. Br will go at this position. Okay, right? So this is very simple. And if you take again H2O here, what happened? It will substitute this. This will leave, and here the OH will come. Okay. Now see, if you have Bu3SNH, okay, tin hydride, and you have taken the light here, then what happened? See here, this Bu3SNH will homolytically break into the radical, something like this, Bu3SN radical and H radical. Okay, and also SNH bond is a weak bond, so that's why this bond will get break as a homolytically. And now the SN has a more affinity toward bromine. Okay, I hope you know this. But if you don't know this, then know this now. So that's why this is our question. So what happened? Bu3SN radical Bu3SN radical will abstract this bromine radical, okay, because the team is a more the team have more affinity toward this bromine, toward the halide, okay. That's why this radical is abstracting the only bromine radical, and after that you will find something like this, okay. So the radical will form again. Again we have Bu3SNH in the molecule, so it will take a radical H radical from here, and you will get a product, right? Okay. Now see, homolysis of Bu3SNH is promoted by the initiator AIBN. Okay. Suppose you have to break this bond as a homolytically, then we use the initiator that is called AIBN, and this is the AIBN. This is the AIBN. Okay. This is the short name of this compound. So what happened if you put the light on this reaction on the AIBN? So what happened? This bond will break as a homolytically, right? As a, and now the N2 will be released, and this is the driving force of this reaction. N2 will be released, okay, and you will get a radical something like this, cyanide radical something like this, and now this radical will abstract H radical from BuSN3, okay. That's why we are using here initiator to break the SNH bond, right? Now this radical will come and take and abstract this H radical from BuSN3, right? And you will get form something like this. And now this BuSN3 radical, suppose we have halide here, this will take halide, okay. See here, if the question is happening here, this radical will taking as a this radical Bu3SN is abstracting the halide Br here, okay. So that's what the use of initiator, to break the Bu3SNH bond, to break the SNH bond, right? Now see, this is also very easy question. We have taken Bu3SNH AIBN. Then what happened? This AIBN will break the Bu3SNH into Bu3SN radical and H radical. Now the Bu3SN radical will abstract the Br radical, right? Then this bond will get a break, and after that you will get form like this, okay. Now see this question, BrCCl3 H mu, okay. So what happened? We have applied H mu, this bond will get break as a homolytically. You will get a Br plus CCl3 radical. Now this will attack on the double bond, and after this it will attack on this Br, and then you will get a product. This is very easy, okay. Now see the next question here, Bu3SNH AIBN. Then what happened? Same thing here. AIBN is helping. AIBN is a initiator, okay. AIBN is a initiator. What will do? It break the bond as a radical SNH bond, and you will get a Bu3SN radical plus H radical, okay. And now this Bu3SN radical, I have considered this as a R group, okay. So this is the Ri. Now this, because we know that the team has a more affinity toward halide, so that's why it will abstract the iodine radical from here, and you will get a form something like this, R radical. And now this R radical will attack on the double bond. Okay, keep in mind always that that R radical will always attack on the on that side on which the radical will be formed more stable. Okay, suppose you have here R radical and you have double bond, and if you attack on this position, okay, then you will find something like this. This radical. Now this radical, okay, sorry. Now this radical is not stable, okay, in the comparison of this radical, right? Because इस रेडिकल के बगल में हमारे पास CN जुड़ा हुआ है. It means it is a more stable. It will stabilize the radical. Okay, so that's why keep in mind like how to do this. Like ये जो हमारा R माइनस है ये हमारा कहाँ अटैक करेगा, यहाँ पे करेगा या फिर यहाँ पे करेगा. सो अगर ये अटैक अगर यहाँ पे करेगा इस वाले पोजीशन पे, then this bond will get break and the radical form on this carbon. Okay, you will get like this, and this is the more stable due to this is a functional group attached here. That's why it will form, and then after just simple you will get like this product. Now see, this is the same question here, Bu3SNH, same question. Yeah, you can do easily here. Okay, so here you have NaBH4 SNI here. We have NaBH4, it means H minus will come and attack and this leave. So you will get a Bu3SNH. Okay, that's not a very big deal, you can do also. Now see this question 1129. In this question we have Bu3SNCl, okay, and we have NaBH4 and we have something like this. So what happens, first of all, you have to do like because we have Bu3SNCl, so this Bu3SNCl will get dissociate into Bu3SN radical plus Cl radical, right? And this radical will go abstract this iodine radical, okay, like this, and then you will form something like this. See here, radical, and because we have here C double bond OMe, and it will attack on this double bond. Okay, right, this bond, एक second, this bond will go now shift on this carbon as a radical, and after that and after this you will form something like this. C double bond OMe, right? Here is a radical, and now this radical will take a H radical from here, and you will form like this, and you will get this. Okay, let me erase all this. You can do try better. Okay, you have to do yourself. Okay, then you can learn. Otherwise it's like just a copy paste. Okay, and after this I have taken here the H plus. So H plus means hydrolysis. So this bond, okay, see here, so this bond will get hydrolyze, and also this bond. So this is basically acetal here, so it will hydrolyze and then form like this. Okay, and after that, because we have acidic medium, so that's why it will form a ring here, intramolecular reaction happen, and you will get a product like this. Okay, now see this one, low energy SOMO are more willing to accept an electron than to give one up. radical adjacent to electron withdrawing group. This point is very important. See here. This line is very important. Radical adjacents to electron withdrawing groups are therefore electrophilic. Okay. A radical adjacent to an electron donating group are therefore nucleophilic. Now see, I am explaining by one example here. Suppose you have Bu3SNH, what will do? It just abstract the Cl radical, okay. After that you will get this, it will attack on this, okay. After that you will get this, right? See here, suppose you have something like this. Here is a hydrogen, here is a hydrogen. Now you have two radicals. Here is a CH3 radical, here is a Cl radical. Okay. So if you see, CH3 radical will abstract this hydrogen radical and the Cl radical will abstract this hydrogen radical, because this hydrogen radical is just adjacent to the electron withdrawing group, right? EWZ. That's why it will work as a electrophilic type, right? That's why here we have taken a nucleophilic radical attack here, okay, because this hydrogen is just adjacent to electron withdrawing group, but here this hydrogen is more far away from this, more far away from this group. So that's why here is a electrophilic radical attack here. It means if you take a Cl radical and the CH3 radical, the CH3 radical will take a hydrogen from here and Cl radical take hydrogen from here, okay. Now see the one more important question here. You have radical initiator, okay. So what happened? See here. So this bond will gonna shift here, right? This bond will gonna shift here, and after this you will form something like this, okay. It will attack on the next molecule on the double bond here, okay. Then this then after that what happened? So this is basically a co-polymerization. It means it is happening. It means it will move more ahead. It will go forward. It means it is polymerization. It is a co-polymerization. It means that the same molecule will go attack. It means undergo many steps. Okay. So that's why we are telling this co-polymerization. Okay. Now see, radical typically react like this. Suppose you have radical here, X radical, and you have two positions here, double bond, and you have here C double bond. What will you do? This radical can attack here also. This radical can attack here also. So you have to attack here. So this is the correct way, right? This is the correct way. Suppose you have CH3 here, something like this. This is the Ame group, right? So this radical will abstract this hydrogen, okay, right? Now see this one. Here we have a X radical. It will abstract the bromine radical from this one, right? So in that way, generally the radical react like this. 1, 2, 3. Okay. Now see, if you have something like this, Li, and you have alpha beta unsaturated ketone, then what will you do? You know that this C double bond O is a hard, right? And we also know that the RLi is also hard. So hard will attack on hard. So that's why you will get here. That's why you will got something like this. Correct? Okay? But if you have here a radical here, then what will happen? It can attack here also. It can attack here also. So here in this case the 1,4 addition is always favorable. 1,4 addition is always favorable. It means the radical will always attack on this double bond. Okay. Now see, radical are very soft species. Their reactions are driven not at all by the charge density on an atom, but by the strength of the bond being attacked and by the coefficient and energy of the frontier orbital. So, radical care nothing for the polarization. So, radical prefer to attack the much weaker CH bond, which because they are unpolarized are often inert toward the ionic region. It means इसका समरी ये हुआ कि जो हमारा रेडिकल होता है ये हमारा सॉफ्ट नेचर का होता है, सॉफ्ट नेचर दैट्स वाई इट विल अटैक ऑन द सॉफ्ट इलेक्ट्रोफिलिक पोजीशन. सो इसीलिए क्या हो रहा है, ये जो रेडिकल है ये हमारा सॉफ्ट पोजीशन पे इस वाले कार्बन पे अटैक कर रहा है, ना कि इस पे कर रहा है. ओके फाइन. Now see one more important question here. Suppose you have something like this Br3, okay, Br3 plus alpha beta unsaturated ketone and plus we have H2. What will happen? What will be the product? See, you know that boron has a vacant orbital, right? It will act as a Lewis acid, right? So what happened? This double bond here, we have a nucleophile here also, right? So that's why what happened? This will attack, right? This will happen. This bond will get attack on the bromine, and because the boron got a negative charge, so to make a neutral, this R1 will leave as a R1 negative and will attack on this double bond. This bond gets shift here and you will get something like this. And after that we have taken H2O here because we know that boron has a vacant orbital here, so that's why it will attack on the boron vacant orbital and this bond will get break and you will find something like this. And after that just do the workup, okay, and you will get a product something like this, right? This is our product. Now see, suppose you have something like this. It means you have Br3 plus O2 plus O2. Which O2 means suppose something O2 and we are doing the reaction by heat or light, then what happens? We know that O2 is something like this, so this will break as a radical, O radical, right? So what we have taken here, O radical, right? So that's why this radical will attack on the boron radical, boron atom in the vacant orbital, and then this bond will get break. Then this bond will get break homolytically, okay, right? Then what happened? See here, this is the vacant orbital of the boron, right? And the O radical is attacking in the boron vacant orbital. This is the SN2 reaction basically. Now the R1 will leave as a homolytically, right? And after that the R1 radical now attack on this alpha beta unsaturated ketone, okay, and then after you will get something like this. And after this you have, because you have Br3 in the molecule, you have Br3 in the reactant. So what happened now? This O radical will attack on the Br3, right? And after that you will get something like this. And after that hydrolysis, you will get this. Okay, see this very carefully, it is very important. You can take a screenshot also. Okay, now see this one. This is also same mechanism. Okay, now this is also a same mechanism. So try to do this on your own self. Then you will fill this question. Otherwise, it's like just a copy paste. Okay, so try this. खुद से ट्राई करना है इसे, है ना. It is exactly based on this mechanism. Okay, now see another question. Okay, see here, suppose you have BU3SNH, we have AIBN, we know that AIBN will work as a initiator, right? So it will break the BU3SNH two radical, BU3SN radical and H radical, right? Okay, so now this radical will abstract the sulfur bond, sulfur atom. Okay, right? So that's what is happening here. See here, this SN radical is abstracting the sulfur radical, and now this bond is breaking as a homolytically. And now, because we have here double bond in the molecule, and we know that this radical will attack here. Okay, this is the intramolecular because this is happening in the same molecule. Okay, and after that it will form like this. Okay, so in such reaction generally 5-member ring is favorable. 5-member ring is favorable. 5-member ring is favorable. Okay, right. Now see. Okay, so so suppose you have here BU3SN radical. Okay, it can abstract the halides. Okay, like Cl radical. Suppose you have Cl, Br, I. It can abstract. Okay, it can abstract these all, and also sulfur also, and also selenium also, ACPH. Okay, so just remember this. Okay, Cl, SPH, ACPH, and like iodine, bromine, these are all can be abstracted by BU3SN. Okay, now see this question. We have BU3SNH and AIBN. What happened? BU3SN radical will come and it will abstract the bromine radical from here and form like this. Now, okay, now what happened? Because we have double bond here, so that's why it will do an intramolecular attack. Intramolecular attack. Yes, 5-member ring is a more favorable. In such case, 5-member ring more favorable. Okay, now you will get a radical here, and after this again it will abstract the H radical from BU SN3H, and after this you will form like this. This is our product. Okay, so here बहुत लोग पूछ सकते हैं कि यहाँ पे 6-member की रिंग क्यों नहीं बनी ऐसे. सो यहाँ पे क्या होता है कि ऐसे रिएक्शन में BU3SN रेडिकल में यहाँ पे 5-member की तो रिंग है ना, 5-member, ये हमारा ज़्यादा होता है फेवरेबल. ओके, जस्ट कीप इन माइंड. ओके, now see this one. This is also same question. BU3SNH, it will abstract the Br radical, and after this intramolecular reaction will happen, it will attack on this, okay, this bond will shift and you will get a major product like this. This is also a same reaction, Bu3SNH. It will obstruct the Br radical, right? And then after it will attack here, bond get here, and you will get a 6-member ring, because here 5-member ring is not a possibility. Here is the minimum 6-member ring and maximum 7-member ring, and we know that 7-member ring is not stable, so that's why the 6-member ring is here favorable. Okay, now see this reaction. This reaction is also based on the same mechanism as I have done here. This reaction, this one. Okay, so try to do oneself here. That's a very good question. Then you will feel, okay, same mechanism as above. Right. Now see, okay, let's see the mechanism. See, first of all we have catalytic O2. इसका मतलब होता है कि ऐसे, right? Okay. Now what happened? See this reaction. See this reaction here. This will attack on the boron and form a R1 radical. Okay. So in the same way, you will get here something like this, ET radical. Okay. And it will take this halides, and then you will form a radical here, and then after it will attack on a double bond, okay, and you will form a 5-member ring here, and after that we have taken here in the reaction, we have taken H3PO2, okay, so that's why it can take H here, H radical from here, okay, and after that it can. So this is your major product. Okay, and these are the side reactions, like phosphorus is a radical here, so you can interconvert into this one. Okay, now again this molecule can attack on the BET3, and you will get something like this, and this chain is continued begin again and again. Okay, it will not stop, right? So this is all about the reactions of the free radical Clayden. There is no question left from this chapter from Clayden. I have sought out, I have taken all the questions, even simple question. Okay, I have done all the questions in my personal notes. This is my personal notes of a Clayden. Okay, I hope this is very useful to you, and if this is very useful to you, then please make sure that you have subscribed my channel. Okay, and please share to your friends so that he or she can get help also, right? So we have done a lot today. I think this is very enough, and now I am also tired. Okay, I have spoken a lot, but this is very necessary to speak, because I want to become a good organic teacher, organic chemistry teacher. So I have to do it. Okay, now I have to work hard to explain the things in very easy way, right? Yeah, I am trying my best from myself. Okay, so yeah, if you have any doubt, you can always ask, okay, in the comment box, right? And yes, I have given the link of my Telegram channel in the description box. Okay, you can go there and check and join. That's a very useful. I have already uploaded a lots of things, PDF, notes, books, all things will be on there. Okay, so don't worry about that. In the next episode, we will bring something exciting topic of organic chemistry. Okay, so please अगर आपको समझ में आया है तो प्लीज़ लाइक शेयर एंड सब्सक्राइब माई चैनल सो दैट आई विल गेट motivate and make more videos like this. So yeah, so please if you have any doubt, you can ask me. Okay, so तब तक के लिए टाटा, बाय बाय, सी यू सून इन द नेक्स्ट एपिसोड सीरीज़. और अभी बज चुके हैं रात के 11:45 हो चुके हैं, 11:45. ओके, तो या तब तक के लिए टाटा, बाय बाय, सी यू सून इन द नेक्स्ट एपिसोड सीरीज़. थैंक यू फॉर वॉचिंग माई वीडियो.